Okay, good morning, everybody. All right, I'm gonna have to keep adjusting the screen as we switch screens here. Um, Welcome on in, everybody. So we kind of finished up the stuff we were talking about last time. Moving into scientific notation. So I have not been seeing questions or anything, so I assume things are going well for students. Of course, if you're falling behind or you're getting confused or you have trouble on the homework or anything like that, please get a hold of me. Just message me in Canvas. Screenshot helps if it's a particular homework problem you're having trouble with. Send me a screenshot or something of the problem. Tell me what you were trying to do, and I can probably help figure out what you're doing. So keep that up, okay? Keep that up. Okay, let's see. Okay, great question. So there's a question here. What is scientific notation going to be used for? That's a great question, because the truth is you don't just use it in everyday life. So some of you will use scientific notation in the future. Some of you may never use it again outside of a math class. So let's get into that. So scientific notation is a more convenient way of representing numbers when you're dealing with really, really, really big numbers or really, really, really small numbers. So they call it scientific notation because it usually comes up in science of some type, right? You're doing research or you're taking classes in chemistry, biology, physics, stuff like that. You can end up with really, really big numbers, right? So for instance, in chemistry, some of you may have done this in your high school chemistry class, where you had to calculate under certain conditions, right? You'd take the temperature of the room and you'd say, okay, it's 74 degrees in the room, and you'd look at the barometer and you'd say, here's the pressure in the room, and you'd have some information about the gas in the room. So like, just air that we're used to is really, we think of it as air. It's really just a bunch of gases, right? You have some oxygen, carbon dioxide, nitrogen, stuff like that. And then in your chemistry class, you might have had to calculate what is the number of air molecules, right? It's sort of loosely air molecules, but we mean that, the gases that make up air. What is the number of molecules inside, say, a cubic yard or a cubic meter, right? Let's use a proper measurement. A cubic meter. How many molecules are there in there, right? This is the thing. I had to do it in high school chemistry. You certainly have to do it in like college chemistry. Calculate that. Well, that's going to be a big number, right? And imagine if it's water. What if you had a cubic meter of water? How many water molecules are in that space? A lot, right? So how do you deal with really, really big numbers, right? If I like, let's just say I gave you a, so if you're watching the screen here, let's say here's our number, 235, and then a whole bunch of zeros. Okay, that number right there, it actually goes off the screen. But that number right there is ridiculous, right? If I give you this number and I say, that's how many molecules there are in a certain size container of a gas, or that's how many suns there are in a specific galaxy, or whatever. There's lots of things. The number of stars in the known universe is going to be a huge number. The number of grains of sand on a beach, huge number. The number of molecules in a room, huge number. If I give you a number like this is essentially like kind of meaningless in a way. Like you look at it and you just go, I don't know. Like I see a bunch of zeros, and I'm pretty sure that's bigger than billions, and it looks bigger than trillions, and that's kind of the last numbers I know, right? We have these terms, hundreds, thousands, millions, billions, trillions. Most people aren't too sure what comes next, right? I'd have to double check. Somewhere in there's a quadrillions. That might be the next biggest one. But this is even bigger than that. So you're kind of like, well, I don't even know the name of something that big. Plus, the truth is most people, like we throw around the term billion and trillion now, especially when we're talking about like budgets for the country and stuff like that. We throw around those terms, but most people don't even have a sense of what even a billion is, let alone like a trillion, right? Like we just pulled people home from the war in Afghanistan. Those two wars, we spent close to $7 trillion. And most people can't even really comprehend how much money is that. It's a lot, but like how much money is it compared to other stuff? It's hard to deal with big numbers, right? Think of it this way, a billion, That's a lot. We think about someone who is a billionaire, and we go, yeah, well, they have some money, but like, do you really understand how much that is? Even just a billion, right? So imagine you have a bank account with $1 million in it. That'd be awesome, right? If all of a sudden you had a bank account with $1 million, you're like, man, this is great. Now imagine having 1,000 bank accounts with $1 million. That's a billion, right? That's large. So when we throw around the term billion, we get comfortable with it and we stop realizing how it is. Imagine having 1,000 bank accounts, each bank account with $1 million in it. That's a lot, right? There's a lot going on there. And this is substantially bigger than that. But if I told you to do calculations with this number, there's a high likelihood that you're going to make a mistake. Why is that? Because when you rewrite this number, the chances of you writing one too many zeros or one too few zeros is pretty high, right? Even me, I'm saying you, but even if I had to write this number down on a piece of paper, I probably would mess up the number of zeros. There's a decent chance, maybe 25%. And if I have to write this a few times throughout the problem, eventually it's going to get messed up, right? So we can see that our regular decimal form for writing numbers doesn't work when we have really, really big numbers, right? Imagine I give you two really big numbers and I say, now go multiply them. Remember how you would multiply multiple digit numbers and you'd have these different lines and you'd do all this stuff? Like a pain, right? So what we want is a better way for writing numbers. So when we're doing, so to the question that was asked, when would I use scientific notation? Some of you won't. Some of you will solely use it in your algebra, your college algebra class, and your calculus class, and then never use it again. Some of you will use it if you're going on to scientific type stuff or you're going to have to take some science classes and stuff like that. You'll use it in there, okay? So it just kind of depends on what you're doing in the future. But this is not a convenient way of writing this number. First of all, I don't want to keep writing all these zeros. And like I say, very good possibility that one time throughout my work, I'm going to accidentally add a zero or have one too few. So what can we do? Well, we introduce what's called scientific notation. Scientific notation takes very big numbers like this. It makes them much easier to write. And here's another good news. Not only is it easier to deal with scientific notation, we will have less mistakes when we do it. Because remember that we use a base 10 number system, right? So what that means is each place in a number represents a power of 10. So if we look at the number 120 or 1,234, think about that number. We have what? This is the ones place. That's 10 to the 0. We have 4 10 to the zeros. 3, that's the tens place. So we have 3 10 to the ones. 2, we have 2 10 squareds because that's hundreds. And then the 1,000, we have 1 10 cubed. So notice how each time we add a place in the decimal system, it's another power of 10. Okay. So what that also means is if we move the decimal in a number, that's the same as multiplying or dividing that number by 10. Right? Think of it if I take 5 times 10. Oops. 5 times 10. 5 times 10 equals 50. So when I took the number 5 and I multiplied by 10, we all know we get 50. But what actually happened here, it really just moved the decimal place because the decimal place originally just followed the 5, right? But now the decimal place follows the 0. So essentially what happened was the decimal just moved over one place. That's one of the keys to understanding scientific notation. When you multiply by 10, the decimal moves one direction. When you divide by 10, the decimal moves the other direction. Okay? So, how can we break down this big number that I have here? Let's write it as scientific notation. So in scientific notation, we usually write this as A times 10 to the n. Okay, that's the proper form for scientific notation. A times 10 to the n. So, but we have some conditions here because we have to keep things strict. You can have numbers that are in scientific notation, and then once you start doing calculations with them, all of a sudden you go, wait, these aren't in scientific notation anymore. Right. So you have to make an adjustment to get them back in the proper form. So for instance, we have a condition for that number a. 1 has to be less than or equal to a. A has to be less than 10. So for your a number that's on there, your a has to be a number between 1 and 10. It doesn't have to be an integer. It could be 5.3. 5.3 is between 1 and 10. It can be 1, but notice it can't be 10. Your number in scientific notation has to be less than 10. So it could be 9.99999, but it can't be 10. Because if you can write a number where your a is 10, you can also write it where your a is 1. And that actually fits into a better format. So your a has to be between 1 and 10. It can be 1. It can't be 10. And we have another condition. And our n is a positive integer. Spelled positive wrong? I did spell positive wrong. Let's see. Looks like I need to put this on the next line. So let's put this whole piece on the next line. I think that'll format a little better. Okay. N has to be a positive integer. So n could be 1, 2, 3, 4, 5, 100, 1,000, 427. It can be any of those. Has to be a positive integer. Oh, wait. Actually, my bad. Actually, it just has to be an integer. Sorry. Is an integer. I was thinking of something else for a second. So it just has to be an integer, right? So, integers, right? So how could we write this then? Well, basically, let's write this number up here in scientific notation. So we know that currently the decimal is over here where the cursor arrow is. That's where the decimal would go. We don't usually add decimals at the end of numbers because it's understood the decimal exists at the end of the number, right? So there's no point in really writing it there. But we need to come up with an a number that's between 1 and 10. So what you're going to do is you're going to take this little decimal at the end, and you're just going to scan through your number, and you're going to go, where could I put the decimal where I would get a number between 1 and 10? Right? So you scan, and then, this is obvious to a lot of people. If it's not obvious to you, that's okay. If this is your first time learning it, you'll get it. Students get scientific notation, and almost always students do. They're able to get these problems correct. But it takes a few minutes because it seems weird. Okay, so you're scanning around. Oh, here, what if I put the decimal right after the 2? That would give me 2.35, and 2.35 is between 1 and 10. Notice if I put it anywhere else, it doesn't work. What if I put the decimal after the 3? Well, that would give me 23.5. But 23.5 is not between 1 and 10. If I put it after the 5, that's 235. That's not between 1 and 10. The only choice is here between the 2 and the 3. So that means our a value here is going to be 2.35. So 2.35. Okay, so that's the a part. We go, okay, so what about the rest of it? Well, if you think about it, how does 2.35 become this number up here? Well, think about what we did a minute ago where we multiplied by a bunch of powers of 10. Well, that's where this part of scientific notation comes in. That's exactly what we're going to do, is we're going to multiply by a bunch of powers of 10. We don't know how many yet, but it's pretty easy to figure out. So we go times 10 to the, now we have to figure out what exponent it's going to be. Hopefully this will still compile. Okay, yeah, there we go. So the decimal was here after the 0, and we changed, oh, wait a minute, what's going on? There we go. Okay, so the decimal was after the 0. Let's move this over. The decimal was after the 0, but we're now writing it where it's after the 2, right? So how many places did we move the decimal? Well, count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. If I counted that right, 28 places. So that means that if we take 2.35 and I multiply it by 10, 28 times, I get this number up here. If it'll recompile. Why isn't it recompiling? On. Automatic recompile on. Okay, so just think about it. Look at this compact version. If you were going to be doing a bunch of calculations with this number and you had to keep rewriting it, would you really rather write it this way with all these zeros, or would you rather write it this way? This one not only has less writing, but since you're writing 10 to the 28th, you're not going to make a mistake on the number of zeros. You're not going to mess that up, which is very easy to do, right? That's like a common thing. You're sitting here counting out zeros and you accidentally leave one out, right? So this number here is this one written in scientific notation. So you should be able to go back and forth. Given a number written in decimal form, can you write it in scientific notation? Given a number in scientific notation, can you write it in decimal form? Okay, can you do that? And can you make that work? Okay. So that's a lot of what that homework is about going through and doing those. So much more convenient, right? Much better way of writing that. So let's continue to take a look at things. What if I had, let's go to the next page. What if I had a really small number? Right, there are different areas of physics where you deal with either really big numbers or really small numbers. If you're talking about astrophysics, you're going to be talking about really, really big numbers. If you're talking about quantum mechanics, you're going to be talking about really, really small numbers. For instance, what is the width of an electron? How wide is an electron, right? I mean, we usually in science, usually you're using the metric system. So a meter, you all know what a meter is. That's in the neighborhood of 3 feet. What part of that would be the width of an electron? Tiny, 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 right? So, for instance, you could have a number like the following. 0.00000000023. Oh, let's make it a little different. 576. Okay, so here we have a number that's really, really tiny. It's really, really small. But notice that we run into the same problem that we ran into with the really, really big number, which is there's a whole bunch of zeros. And if I have to keep writing this number, at some point I'm going to add a zero on accident, or I'm going to leave a zero out, and it's going to be a problem. So what do? You play the same game, except realize the decimal's going the other direction. In other words, in this case, we're dividing by 10, right? So just so you can see that example like we did last time, what if we have 5 divided by 10? And we end up with what? 0.5. See how you kind of have the same number, it's just that the decimal place moved there on us. So the decimal was behind the 5, now it's in front of the 5. That happened because we divided by 10. So when you multiply by 10, the decimal moves one direction. When you divide by 10, the decimal moves the other direction. Okay? So we're going to do the same thing, but for this really, really tiny number. So play the same game, take the decimal and scan it in this number and ask yourself, where can I put the decimal place that's going to, where can I put the decimal place that's going to give me a number between 1 and 10? Remember, your A has to be between 1 and 10. Well, looks like here between the 5 and the 7, right? So my A is going to be 5.76 times 10, and then we have to figure out the power that 10's going to go to. Well, in this case, we're dividing by 10, so we're going to end up with a negative exponent, right? When we were doing the last one, we were multiplying by powers of 10 to make the number bigger, so we were multiplying by 10. Now the number is going to get smaller. 5.76 is a bigger number than the one we're trying to represent. So we have to do divisions by 10. So how many divisions did we have to do? Count the number of places that the decimal moved. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 places. So that, whoops, I got to make that negative. And there we go. A better way of writing that number. We're going to make less mistakes by writing it that way. It's also less writing, significantly less writing, right? You talk about like one of the numbers they have in chemistry is called a mole. It's like, if I remember right, it's how many molecules under standard temperature and pressure and all these different things there are in like I don't know what it is, a cubic meter or something like that. It's a mole. It's a really big number. It has like 23 decimal places or something like that, right? It'd be a pain to write in decimal form, not too bad to write in scientific notation, right? So just be able to go back and forth between these two, always remembering that your A should always be between 1 and 10. Okay. Now, sometimes what will happen, like students pick that up pretty good, but there is one thing that's confusing that leads to students missing points on homeworks and sometimes missing partial points on a test. And that is, you might start with numbers that are properly in scientific notation, but as you do calculations with them, the numbers stop being in scientific notation. Well, if we can see that there's a benefit to using scientific notation, then whenever we're doing a calculation and our numbers stray from scientific notation, we should put them back in scientific notation, right? There's a tendency for people to go, well, they're kind of close. They're kind of like scientific notation. Kind of isn't good enough, right? It's you're either in scientific notation or you're not, right? It's not one of those things where you can kind of be doing it. And it might seem like, why are you being so strict about scientific notation? It's because when we're using large and small numbers and we stray from scientific notation, the chances of you making mistakes goes way up. And what's the point of doing mathematics if you're going to make mistakes? I mean, mistakes are fine as part of the learning process, but if you're doing actual work that's important for a business or for a research, you don't want mistakes in your work, right? You want to be able to go back and be confident when you check things that everything was done properly. Okay, so let me give you an example. What we want to do is look at multiplying scientific numbers that are in scientific notation. And the good news is the multiplication and division for scientific notation is pretty easy. Okay, once you see how to do it, it's not too bad. So let's say we have the following numbers. Oops. I don't want to do the general. Well, yeah, let me write the general formula, and then we'll write the actual, then we'll do an example. So how do we go about multiplying numbers that are written in scientific notation? So this is just your general formula, right? This is some number written in scientific notation. This is another one written in scientific notation. What would we do? Well, if you think about it, a number written in scientific notation is kind of already a multiplication, right? We'd like just look at this, look at our example that we did here. This one number is actually two numbers being multiplied together. It's 5.76 and it's 10 to the negative 19. Multiply those together, you get your answer. So scientific notation is already two numbers being multiplied. So if we're multiplying two numbers in scientific notation, we're actually multiplying four things together, right? And remember, one of the nice things about multiplication is that it is commutative. What does that mean? That means we can multiply them in whatever order we want, right? It's not like subtraction where if you do it in the wrong order, you mess it up. Multiplication, you multiply your numbers, at least for the real numbers. You multiply them, they're going to come out either direction. So what that means is I can choose the order I want to multiply these. So what happens is I'm going to multiply the A and B together first. Those leading terms that have to be between 1 and 10, I'm going to multiply those together first. And that will give me AB. And then think back to your exponent rules. What would 10 to the m times 10 to the n be? Do we remember? That's going to be 10 to the m plus n. You're going to add those exponents together. Okay? So there's your formula. That's how you're going to do it. So let's do an example. I'm going to do a couple examples, but all right, let's say we've got 2 times 10 to the 9th, and then I've got 3 times 10 to the 7th. What does this equal? Well, my a and b are a 2 and a 3, right? So I should multiply those together to get 6. So I've got 6 times 10 to the, and now I'm supposed to add those exponents together. So 9 plus 7, 16. So 2 times 10 to the 9th times 3 times 10 to the 7th is going to be 6 times 10 to the 17. Okay? So not too bad. That's how that works out. Yeah, right. So do that. So that was easy, right? That was pretty straightforward. You go, okay, that's a really easy formula. I basically already, I'm sort of, I know my students when they're watching this, they're like, yeah, okay, I got it. There's nothing tricky about that. That's pretty straightforward. And if you're still kind of struggling with it, that's okay. But most students pick it up pretty quickly. Let's look at one that's a little more complicated. Let's say we've got 4 times 10 to the 11th and 5 times 10 to the 13th. Okay, so I want to multiply these together. So we're going to follow the same rule that we just did, right? So I go, okay, 4 times 5 is 20. So I get 20 times 10 to the, okay, 11 plus 13 is 24. So we say, okay, that was easy. I did it. I'm done, right? There's a problem here. I'll give you a second just to see if you can, in your own head, figure out what's the problem here. And the problem here is we're not in scientific notation anymore. This number is not scientific notation. Why not? Remember, your a in front is supposed to be between 1 and 10. And I know this seems like, why are you being so why are you being such a stickler about this? Like, what's the big deal? It's a 20 now. Can't we move on? And the answer is no. You have to be able to adjust numbers to be back in scientific notation, because when you're doing your chemistry lab report and writing it up, your teacher's going to say, these numbers should be in scientific notation. Why are they not in scientific notation? You go, well, because they used to be, but then I multiplied them. You go, yeah, so then you put them back in scientific notation. There's really good reasons why we do that. So we have to make an adjustment here. So what you have to do is basically realize, okay, we're going to play the same game that we were playing before with the decimal place. So the decimal place is currently behind the 0, but I want to move it over to be behind the 2, because then if it was 2.0, then we would be back to that situation where 2 is between 1 and 10, right? So you can think of it this way. What we're essentially doing is stealing a power of 10 from this number and moving it over to this number. So it's still balanced. That 10 didn't disappear. Sometimes students do that where they're like, oh, now I'll just make this 20 into a 2. No, you can't just make the 20 into a 2. We can adjust this number. Basically over here we divide by 10, but then to balance over here we multiply by 10. So what I'm going to do is I'm going to say, okay, well then this should become 2.0 times 10 to the, right? Give you a second to sort of see if just in your brain, can you figure out what this number should be? If we took a power of 10 from 20 and we transferred it over here, and this is keeping track of how many powers of 10 we have, then this should now be 10 to the 25. Does that make sense? We basically moved a power of 10 from the A part over to the power of 10 part. And now we're back in scientific notation. Great. You're going to get full credit on your chemistry lab report. You're going to make less mistakes because you're keeping things in scientific notation. Everything's good. And it's easy to check your work. Think about this. If I wrote the number 20 followed by 24 zeros, would that be the same as writing the number 2 followed by 25 zeros? Yeah, that should come out to be the same, right? So you go, okay, good. I made my conversion correctly. So sometimes there's a little bit of, when you're doing these conversions, just double check. Just think through the problem and go, did I do that right? 20 with 24 zeros, 2 with 25 zeros, is that the same? Yeah, that should be the same. Okay. Now, so is there questions on that? We'll do a little bit more of this as time goes on, but I have a couple things to mention. So if there's questions, throw them up there. One thing that I see people doing, and I've seen this in textbooks, and I hate when textbooks do this, they have you memorize. Remember, we would sometimes move the decimal to the left, and we would sometimes move the decimal to the right when we were doing our conversions of our numbers for scientific notation. You'll see textbooks that have you memorize when to move the decimal left and when to move the decimal right without any kind of justification or logic as to why you do that. And what I find for students is that's not a good way to think about it. So if you've done that in the past, if you learned it that way, or you're seeing it now and you're learning that way, I think I haven't looked at it for a few days, but let's just look. I think maybe Delta Math, I don't like the way they do it. Let's see. Let's look at a problem. Actually, just want to see there. Yeah, show an example. Yeah, so here they kind of say move the decimal places to the left. They're being a little vague. Like, why do I move it to the left? Why in another one do I move it to the, like here they're saying move it to the right. Well, why am I moving it to the left or right? So a lot of times what happens is students will memorize it and they'll say, okay, when I see this, move the decimal place left. When I see this, move the decimal place right. The problem with mathematics education is that when people memorize something but they don't really understand it, they don't remember it and they mix it up. So I see students who do that. They'll move the decimal the wrong direction on a test and then go, oh, I thought I knew how to do that. But that's because you memorized it with no context, right? So what you want to do is ask yourself, should the number get bigger or smaller when I move the decimal place? So for instance here, 2.35 times 10 to the 28. Just ask yourself, if I start with 2.35 and I start multiplying it by powers of 10, should my number get bigger or smaller? Well, if I'm multiplying by powers of 10, my number should get bigger. And that would inform you, oh, okay, so I should be moving the decimal place to the right because that makes it bigger. That's that intermediate step that people like to skip, but I also see it cost people a lot of points. So I think hold on, let me fix something here. I was in a meeting the other day and I had to change my background, but I don't like the way it's looking right now. It's like blurring my hands and stuff. Well, let's just go with none. There we go. That's at least a little bit of an improvement. Okay, so just add that little extra step of critical thinking where you go, oh, 2.35 times powers of 10, that number gets bigger. So I'm going to expand to the right. When you're down here, 5.76, if I multiply by 10 to the 19th, my number should get smaller. So see, then I'm expanding to the left of the number. If you always ask yourself the question, should my number get bigger or smaller from here? Then you're not going to go the wrong direction, left versus right. But I see people do that when they just try to rely on memorization, which I know many of you came through, not all of you, but some of you came through educational systems where you were taught that that's what math is, where you just memorize things. But that's probably why some people struggle, is because the research shows we're not supposed to be teaching math that way. That's That's a good way to not be good at math, is to just memorize stuff and not understand how it works. So if you can remember that, just ask your question, when does it get bigger, when does it get smaller? That will inform you as to which direction to move things. Okay? And that's the multiplication. So let's look at a problem here. So let's look at, let's do a couple here. Okay. Write 1.8 times 10 to the third in standard notation. So I go, okay, well, that means I'm going to move the decimal 3 places. Should I be moving the decimal 3 places to the left, or should I be moving the decimal 3 places to the right? Well, I go, well, 1.8, if I multiply that by 10 3 times, my number should get bigger, right? So I'm going to move it in the direction that makes things bigger. So 1, 8, 0, 0. So it's the decimal started here at 1.8. I've now moved it 3 places to make a bigger number. 1, 2, 3. And there we go, green check, right? Let's see, is the next one, what's the next one going to look like? Here we go, good. Now we got one with a negative number. So, okay, 7.9 times 10 to the negative 2. So I have to move the decimal 2 places. Now I have to think, am I going to move it left or right? Well, if I'm looking at this, 7.9, 10 to the negative 2, when we have a negative exponent, that's the same as dividing by 10, right? Because 10 to the negative 1 is 1 over 10. So it's the same as dividing by 10. So if I take 7.9 and I divide by 10, and then I divide by 10 again, do I expect the number to be bigger or smaller than 7.9? I expect it to be smaller. So that's the direction I'm going to change. I'm going to move the decimal. So 0.079. So the decimal was between the 7 and the 9. It's now moved 2 places. And there we go, correct answer. Okay, so that's how you do those. Let's do it the other way. Convert number to scientific notation. Okay. And they've got the different boxes you're going to fill in here. Write the number 5,800 in or 5,800 in scientific notation. Okay, so I have to think, where am I going to get the number to be between 1 and 10? 5.8, right? That's the only place I can put the decimal where it's going to work. So 5.8 times 10 to the, now we have to ask ourselves, how many places did I move the decimal? Where it went from here to between the 5 and the 8? 1, 2, 3. So it's going to be times 10 to the third. If I take 5.8, I multiply it by 10 3 times, I get 5,800. And there we go. Okay. I think that's good for those. Let's go back. So let's look at multiply and divide. So in this one, let's see, this isn't a great problem. Let's see if we can get a better one. You're probably going to want to use a calculator for this because they're giving you numbers that give you calculators. Let's go back to the original problem. Basically, in this place, like, they're kind of giving you ridiculously small numbers. If you were dealing with 73, you're probably not going to use scientific notation, right? This is usually, you use this in science and stuff when you're dealing with at least in the thousands and probably more like tens or hundreds of thousands. Then it makes sense to start using scientific notation. Probably not if you're talking about the number 73, right? But you'd make it 7.3 times 10 to the 1, and then you've got 4.4 times 10 to the 6th, and then you would multiply those out. So let's do that in oops. I don't have my calculator with me. Let me see. I think there should be one on here. Show up on there. So, in fact, let's switch over to, so 73 and 4.4 times 10 to the 6th. Okay, let's do it here so I can show more steps. So 73 and 4.4 times 10 to the 6th. Did I get that right? 73, 4.4 times 10 to the 6th. Okay. So then I'm saying, okay, but what this really is equal to, let's put them in scientific notation, is 7.3 times 10 to the 1. Now, we don't usually write the 1 exponent. I'm just writing it there so that you can recognize, yeah, that's actually in scientific notation. Plus, if we don't write it, sometimes people add a 0 instead of a 1. So you have to be careful. Make sure you realize that's 10 to the 1. And then we've got 4.4 times 10 to the 6th equals, let's do this on the next line. Okay, so then in my calculator, I'm going to go, okay, I'm going to multiply the A and B part. 7.3 times 4.4 equals 32.12. 32.12, that's my AB part, times 10 to a power. And remember, this is like I mentioned, sometimes when people don't write this as 10 to the 1, because we usually don't, they go, oh, well, 6 plus nothing is 6, right? But really it's a 1 here, so 6 plus 1 should be 7. So this really should be to the 7th power. Okay, now this isn't, we're not done, right? We just multiplied those numbers together. And I'm pretty sure it's going to reject our answer here. So this is wrong, but I want you to see what it looks like when it's wrong. So if you do that at home, you go, oh, that's right. He did this in class, and I know how to fix it. So I'm going to show you. So 32.12 times 10 to the 7th. 32.12 times 10 to the 7th, and it should tell me I'm wrong. It says, nope, your answer is incorrect. Try finding your mistake. You have 1 attempt remaining. So it told me I'm wrong. I forgot. I don't know why I was thinking it was going to give me a hint or whatever. But like, this isn't right. Why? Because this number is not between 1 and 10. So we have to make that adjustment. Okay, I'm going to move the decimal 1 place over here. Essentially, I'm dividing this front part by 10. But to balance it, I have to multiply this part by 10. So really, we want to make this 3.212 times 10 to the 8th. This number got reduced by a power of 10. This one got multiplied by a power of 10, so it works out. Submit. There we go. Okay, see how that works? And they did the same thing in here. They got down to where they had, actually in this case, they did it slightly different. They didn't convert the first number to scientific notation. Again, it's kind of weird because you probably wouldn't use scientific notation with 73, but it's in this section, so I'm showing you. So the way they did it is fine. The way I showed you is fine. Like, you get there the same way. Okay? Now, how do you do division? Let's see. Is it going to give us a division one? Okay, what is the quotient of 7.2 times 10 to the 8th and 3.6 times 10 to the 5th? This shouldn't be any surprise. You're going to divide 7.2 over 3.6, which will give us, what, 1/2? And then you'll subtract the exponents. So for multiplication, we added the exponents. Now you're going to be subtracting, right? So when we do 7.2 divided by 3.6, we're going to get 2. So this is, I think this will be 2 times 10 to the 3rd. Yep. So see how it works? You're dividing the A and B part to get 2. You're subtracting the exponents to get 10 to the 3rd, and your final answer, 2 times 10 to the 3rd. So if you understand the multiplication, the division's the same thing. It's just that you have to subtract instead of adding. Now, one thing to be careful about here, what can happen is your A can end up being too small. So it can be less than 1, and all you do is you make that adjustment. Like we've been adjusting that A value. You make the adjustment, and then you're good to go. Okay. Yeah. So, okay. So that's how scientific notation works. So you should be able to go ahead. So I think there's not much more to say about it. So here's what I'm going to say. If there are questions from this section, of scientific notation, send them to me. Send me some screenshots or something and say, you know, I'm really struggling with this section. And then I'll have a couple, I can do some next time. But if everyone's blasting through this and doesn't need me to go over it, we don't need to spend time on it, right? So I will assume we don't need to spend time on it, but don't feel bad if you need to see more. Like, don't feel like, oh, I don't want to hold up the class. It's not like that. If anyone's struggling with these sections down here and isn't getting how to do that, we have time that I can cover an example or two next time and help you out with that. Okay, so let me know. Otherwise, we'll go into rules of exponents because that definitely is confusing for students, and we'll want to. That's going to take multiple class sessions to get through. Okay, so we'll do that. So as always, anyone who wants to jump into Zoom and talk to me, go for it. Otherwise, I'm shutting down the stream.